Hello everyone, welcome to this instructional biochemistry video. The topic that I will be going over today is enzyme inhibition, and I wanted to start with classifying the two main types of enzyme inhibition. So there is irreversible and reversible inhibition. So irreversible is where the inhibitor binds covalently to the enzyme. And reversible is where it binds non-covalently. So the covalent bond for the irreversible inhibition is essentially a permanent bond. So it renders the enzyme permanently unusable, right? And so the two main types of this is simple irreversible and suicide inhibition. This is not the main focus that we are going to be talking about today. We are going to be focusing on the reversible inhibition, which is where the inhibitor binds non-covalently, which is essentially a non-permanent bond and will allow the enzyme to still be functioning, but it just functions less effectively than it would without it. So there are four main kinds of this reversible inhibition. The first that we're going to be going over today is competitive inhibition. And so this is where the inhibitor binds at the active site, right? So it essentially is competing with the substrate for this active site for bonding to the enzyme. And so when the inhibitor is bound, it blocks the substrate from doing so. This can be overcome by increasing the amount of substrate. So if we have more substrate, or if we increase the substrate to inhibitor ratio, that means that it's more likely that the substrate will bind versus the inhibitor and will essentially overcome this type of inhibition, right? Now, because this inhibition is able to be overcome by the substrate amount being able to outcompete the inhibitor, this means that the max velocity, or Vmax, is not altered. However, this type of inhibition does cause the Km, or the concentration of substrate required to reach half of the maximum velocity. This value is increased, which points to the affinity decreasing. And this is because the substrate concentration has to be higher to reach half of the maximum velocity, because you need to increase that amount to outcompete the inhibitor, right? And so if we are to look at this in terms of a Lineweaver-Burke plot, so we'll have this here. So if this, let me add this. If this guy here is the uninhibited substrate, or the uninhibited enzyme, then this right here is what this type of inhibitor will look like. So they will have the same y-intercept or the same Vmax, but they will have different x-intercepts, which corresponds to the increase in the Km value. So the second type we'll be looking at is uncompetitive inhibition. And this is where the inhibitor binds to the enzyme substrate complex itself. And this will be at an allosteric site. It won't be at the active site because the active site is being taken up by that substrate. And so what this essentially does is it locks the substrate in, which increases the affinity between the two, and actually allows the binding site for the inhibitor to form. So in this type of inhibition, both the Km and the Vmax are lowered. And this is because the enzyme substrate inhibitor complex, so the inhibitor being bound to the ES complex, is more stable than the ES complex. So the equilibrium is shifted to the enzyme substrate inhibitor complex, which means that the affinity or the Km, so the affinity is increased, which reflects in the Km being decreased. And the Vmax is lowered because that substrate is locked into the enzyme. So if we look again at the Lineweaver-Burke plot for this guy, if we are calling this the uninhibited enzyme, then this next guy will be the inhibited enzyme. So the slopes are the same, they're parallel lines, but both the x and y intercepts, or both the Km and the Vmax, are different values. The next type of inhibition is mixed non-competitive inhibition. So this kind of inhibition is when the inhibitor binds to either the enzyme or the enzyme substrate complex. But in mixed non-competitive, which differs from pure non-competitive, which is the next and final kind of inhibition, the affinity for each of those two differs. And so because the affinity is not always the same, that means that the Km also differs depending on that affinity. Because that's just kind of the definition of what the Km is, right? It's kind of a value of affinity. And so if the inhibitor prefers binding to the enzyme, Km increases. And if it prefers to bind to the enzyme substrate complex, Km will decrease. And so if we, again, look at the Lineweaver-Burke plot for this guy, if we are calling this the uninhibited enzyme, this is what the inhibited is going to look like. So both the Km and the Vmax, or the x and y intercepts for these two, are different, but they do cross at a location that is not on an axis, right? So that's kind of how you can tell if it's mixed, non-competitive versus the other types of inhibitors. Then the final type is pure non-competitive. So it is the same general concept as before, except the affinity, or the inhibitor's affinity for the enzyme and the enzyme substrate complex are the same. And so this makes this a very rare kind of inhibition because it's pretty unlikely for the inhibitor to have the exact same affinity for both. But it does exist. It is seen. So when the enzyme conformation is altered by the binding of that inhibitor, adding more substrate will not be conducive to forming the ES complex. Or in other words, adding more substrate won't affect ES formation or the enzyme substrate complex formation. And so because there is less enzyme available to react, Vmax decreases, but Km is not altered because all of the active copies of the enzyme still have the same affinity. So if we were to look at this final Lineweaver-Burke plot here, if we are calling this the uninhibited enzyme, we will call this the inhibited enzyme. So because Km is the same, they both cross at the same place on the x-axis, but the Vmaxes are different. So they have different y-intercepts. Thank you guys for tuning in. Go Notre Dame. And if you are a Notre Dame student in Chem 40420, I hope that this video helped you out a little bit. I hope you have a good rest of your day and a good rest of your studies.